And I'll be talking about something slightly different, right? So it's about coherence and overlaps, but we'll see there's a connection with contextuality, and that's the reason why I'm here. This is based on some work that I did together with Daniel Brod from Universidade Federal Fluminense in Brazil, and on work that's in progress that I'm doing together with Rui Soares Barbosa at INL. So this is the outline of what I want to tell you in a locality. Then I'll work through some examples and I'll come to some conclusions. So that's the plan. So first, projective unitary invariant properties. Okay, these are properties that are invariant under unitary transformations if you apply the same unitary to each state in the set. And they are invariant under gauge choices, like changing the global phase of each state. So we all know that, for example, if you have three real vectors, if you rotate them, the angles between them don't change. So this is an example of such a property. So these properties are geometric in character, and they are relational in character. They have to do with the way that the states are oriented with respect to each other. So there is a mathematical result, which is quite neat, that says that all the projective unitary invariant properties of a set of states, they only depend on k-state Bargmann invariants. So they can be characterized if you know these quantities. And these Bargmann invariants, you can see the expression here. They are the product of inner products, okay, of states in a cycle. So inner product A with B, B with C, C with D, and so on, until you go back to A. So it has to be a cycle. So this is shown in this paper here, but actually there are some results on that of a more mathematical nature, which are quite old. So these appear many places in quantum mechanics and even in classical mechanics, if you adapt this, okay, for not for quantum mechanics, of course. For example, in the study of geometric phases and photonic indistinguishability. So here there are some references, okay, talking about geometric phases and how to measure these things in photonic systems. Okay, so these are the invariants that we care about. But here in this work, I'll be discussing everything that I'll talk about is about the overlap. So the overlap is the Bargmann invariant of just two states. So that's the inner product of A with B times the inner product of B with A. So it's the modulus squared of the inner product of the two vectors. If you have mixed states, the expression is like this, as a trace of rho A, rho B, okay? So this overlap, it's playing the role exactly of the angles that are in this drawing, right? Because it's related with the inner product in this way. So the overlap, you can estimate the overlap. If you have a description of state A and an apparatus to measure a projector to state B, by just doing that, you prepare a state, measure B, and see the probability. That's the overlap. Or you do vice versa, it's the same thing, it's symmetric. But even if you don't have a description of the projector onto A or the preparation of B, you can do a measurement of the swap of the overlap using the swap test circuit, so which is shown here. Okay, so you input these two unknown states, and the probability of measuring 0 in this auxiliary system gives you the overlap, as you can see here. Okay, and that's why if you do this for mixed states, you see that you get the trace of rho A, rho B, or projector of phi, projector of psi. Okay, so this is the quantity that I'm interested in because it can be measured and because it's relational in nature. So now let's look at the simplest scenario. When you have a set of states, you just have 3 states, okay? And you assume you have sources of these 3 states, and you use swap tests, for example, to measure the overlaps that you have. So you can represent these overlaps. There are 3 overlaps here, AB, AC, and BC, in a triple of overlaps, okay? So here we have. And in this paper, we showed what are the boundaries of the quantum set. So which overlap triples are reachable by quantum states. And this set is shown here on the left, okay? And you see it's a convex body, but it's not a polytope, okay? But the interesting thing is when we compare this set with a different set, which is a set of overlaps that you can reach with classical states. That is coherence-free states, states that are diagonal in a single reference spaces that have no coherences, okay? And that's where the notion of classicality will appear here. So our definition of classical state is a coherence-free state. It's a diagonal state, an incoherent mixture of states in a fixed reference spaces. So for these states, you have a global density matrix, which is diagonal. You have the local density matrix describing each system, which is also diagonal. And the overlap is just a trace of these two diagonal matrices. And you can show, as I do here, that the probability that this is equal to the probability of equal outcomes of the reference observable, which is the observable that is diagonal in the same basis as all the states. So here's this example. We have just two states, two-dimensional states, which are diagonal. And if you compute the overlap between them, it's just the product of these diagonal matrices. And you see in this expression here that it's just the probability of getting the first outcome of the first state and the first outcome of the second, or the second, or the third. That is, it's the probability that you get equal outcomes when you do the measurement of this reference observable on the two different systems you have. So if you think a bit about this, you see that what I'm doing is kind of it's a quantum mechanical parameterization of a general probabilistic process, right? There's nothing quantum when you're looking at these diagonal states. You're just describing a general way of preparing probabilities to be output by measurements, which are fixed, by preparing states which are diagonal, okay? So they are classical states, actually. That's why we call them classical. So these are the classical states we want to compare the situation with. And it's easy to work out what the reachable region for the classical states is for this three-state scenario, okay? Three overlap scenario. In this overlap space, okay, it's clear that there are three states, three deterministic states for the overlaps that you cannot reach, and these are these three in red here. Why you can't reach? Why you can't have these states? Because this would break the transitivity of equality. Because a state that is like 1, 1, 0 is saying that A equals B, A equals C, but B is different from C, and that's a logical impossibility. You see? So these three states, which are drawn red here in this cube, they are forbidden. And the allowed states are these 5 states, which are okay. They correspond to like all states being different, or all states being equal, or maybe one pair being equal only, right? And these states are the 5 states in green. So if you want to know what possibilities there are for classical states, for these three overlaps, they are the polytope formed by the convex hull of these 5 states, and it's drawn here, okay? Now it's clear to see that we have 3 non-trivial facets of this polytope, and they are of this type, okay? One overlap plus the other minus the third is less than or equal to 1. Okay, so these are the classical overlap inequalities that we want to find, and we already found, right, for this simple scenario with 3 states and 3 overlaps. Now, what you can do, okay, in with different physical systems is prepare states and measure their overlaps. So by doing that, you're not measuring anything that's particular to that state. You're not tomographically reconstructing it. You're just measuring the relational properties, the overlaps between states. And when you do that, you can find states which are outside of the polyhedron on the right and somewhere in the convex body on the left, like this little green point I drew here, okay? So if you find a state like this, if you obtain such a triple of overlaps, you have a basis-independent coherence witness. You see, because if you obtain these 3 overlaps from your experiments, you know that there's no single basis that diagonalizes the 3 states simultaneously. So these states, they must have some superposition, okay? And you were able to say that without measuring them separately. So these witnesses have been measured recently in a photonic setup in this paper where we collaborate with Fabio Sciarrini's group in Rome. So these are the overlap inequalities, and I'll show how we can find others. But I'd like to now introduce the reason why they are contextuality inequalities, okay? So as I mentioned, looking at these coherence-free states is just a roundabout way of talking about general probabilistic processes. So you can describe this in a more operational description, looking at a general scenario in which you have vertices being measurements, and overlaps, edges being overlaps, probabilities that the two measurements linked by the edge yield equal outcomes. Okay, so you can think of these vertices as probabilistic processes and the edges as the probability that the processes give the same outcome. Now, a classical model, okay, here is a model that specifies everything. You have a global probability distribution function for all vertices, outputs, and you have the correct marginals for the single vertices and for the two vertex contexts that we have. Okay, so this global probability distribution gives the outcomes of everything, and in particular of each vertex and each pair of vertices, which are linked by an edge. So what we discussed before, these coherence free states, they're just a quantum realization of this classical model that I'm describing in more operational terms. This realization is given by diagonal density matrices, which are measured in a reference observable that just reveals pre-existing properties. So actually, there's much more information you can get by measuring any context you like, but I'm focusing on the contexts which only involve two vertices at a time. So notice that I'm already talking about this in a language that is reminiscent of contextuality. And actually, it's clear to see that this classical model is a non-contextual model because by specifying the global diagonal states with the local diagonal states with the right probabilities in the diagonals, you are specifying a model which is non-contextual and for which the probabilities are determined and are revealing these properties which are, ontic, they exist and they are fixed, predetermined before the measurements. So these classical overlap inequalities that I just described for the simple scenario, they are contextuality and non-locality inequalities. So I would like to show you some examples where you can see clearly what the correspondence is and how this interplay works. So for the case cycle scenario that we heard a lot about, right, by many speakers today, by Etiba and many others, we found these overlap inequalities, okay, just thinking about logic and before realizing this was related with contextuality. So these overlap inequalities are the cycle inequalities when you have k vertices in a cycle like I drew here. And of course, I'm already pointing out to some places where this is discussed, like the Hardy and Abramsky paper on logical bioinequalities and the Cabello, Bodroni, Mateus, and so on, paper on n-cycle inequalities. But if you want to know what inequalities are obeyed in more general scenarios, you can do this because you can find all vertices, all classical vertices, deterministic vertices, and find the classical polytope. And the way to do that is first to list all the set of deterministic 0 and 1 assignments for this overlap M tuple. Okay, so you write all vertices which have either 0 or 1 for each of these overlap values. Now you delete all the M tuples which are forbidden by logic, by transitivity of equality. So you have to check all possible cycles because each cycle you have may forbid you from having 1, 1, 1, 1, 1 and a single 0 in the cycle. Okay, so if this happens, you eliminate that vertex. So when you finish, you will have the equivalent of these green vertices, but in this more general scenario, which are the allowed vertices for these overlaps. And then you can determine the convex hull of these allowed vertices to find the facets that describe this polytope. Okay. And if you violate any of these facets, you have a witness of coherence, contextuality, and non-locality, depending on how you implement this process. So here are some examples, okay? This is the 4-cycle scenario. You have, in the overlap language, you would have just 4 states, and you have the 4 overlaps between neighboring states in this square, okay? You can think of this, well, talking about the operational description of this thing, you have 4 probabilistic processes, okay, which are dichotomic. They have plus or minus 1 outcomes. And if you write the overlap as the probability of these processes giving the same result, then the overlap is related with the expectation value, the correlation function in this way. Okay, this is the probability of getting the same outcome, and you can write it as a function of the expectation value for the correlation function. So if you look at the overlap inequality for the square, this is the overlap inequality you get. Okay, a single minus sign here, and this corresponds to the CHSH inequality, right? That's why I labeled the vertices A1 and A2 in the diagonal. They are the measurements that Alice will do, and B1 and B2, the measurements that Bob will do. You can look at the 5-cycle scenario. Well, we've looked at it many times already, right? I'm just talking about this overlap language. You have these observables, which are, well, these processes which are dichotomic. They have plus or minus 1 outcomes. The probability that 2 neighboring processes gives the same result is the overlap, and it's associated the same way with the expectation value. And you translate this inequality, the overlap inequality, into the KCBS inequality. You can do the same thing for larger cycles, okay? And obtain equivalent n-cycle inequalities or equivalently chain Bell inequalities, okay, of Brownstein in caves. So these are some of the inequalities that we find from overlaps and equivalence in contextuality and nonlocality inequalities. You will notice that I jumped to the 4-cycle and the 3-cycle and the 5-cycle before going to the 3-cycle. And that's why, because the 3-cycle, you have to have a bit of a sleight of hand, okay? Because you have 3 processes. If you want to implement this thing quantum mechanically, you need to be able to estimate this probability that the processes give the same result. So they must be compatible somehow, right? So one way to enable you to measure these things and see the outcomes and check how often they are the same result is to double this space by using an entangled state, maximum entangled state. And now you can do, for example, the measurement of PA at Alice and the measure of PB at Bob. I'm calling this B line, right? B prime at Bob. So the graph that you end up with when you duplicate this thing is like this, and which enables you to estimate the overlaps in this blue region, because then they will be associated with the expectation value of the corresponding observables, projectors onto Alice and Bob. Since we have the perfectly anti-correlated state here, singlet state, the overlaps on the left here, they are the probability that the outcomes are different, right, in this singlet state. Or you could use the other state for which it would be equal. So this is the way you relate the expectation values in the Bell test with the overlaps on the triangle overlap scenario, okay? So I collapsed again this graph into triangle because I'm identifying A with A prime, B with B prime, and C with C prime because of the perfect anticorrelation that you're assuming holds. So if you check exactly the assumptions that I'm using here, that anticorrelation is holding that you are measuring an entangled pair of qubits, the overlap inequality translates exactly as the original Bell inequality, the first Bell inequality that Bell derived, which has 3 settings. And for which, assuming perfect anti-correlation, you have exactly this inequality in terms of expectation values of +1 - 1 outcome observables. Okay, so all of these cycle scenarios for overlaps, they correspond to either Bell tests or contextuality tests, right? So we do have other scenarios, okay, that we can consider. And this is a slightly more complicated scenario with 4 states, in which we are allowing, we're including all the overlaps possible. So this is a complete graph of 4 states, okay, or 4 probability processes, okay. And when you do that procedure by finding all the allowed deterministic states, eliminating the ones that result in a logical impossibility, finding the facets, you obtain many facets, which corresponds to all 3 cycles and all 4 cycles of this therefore cycle for this scenario. But you also find a new facet, and the new facet is written here, okay? It's just the sum of green overlaps minus the sum of red overlaps has to be smaller than or equal to 1, okay? And if you want to violate this in this overlap way of interpreting this inequality, you just need to find 4 states which violate this inequality, okay? And these states need to be only 4-dimensional at most, because you only have, well, that's the maximum dimension of the spanning subspace that 4 states can be, right? So for these particular states that I have here, they are Q-trig states. We seem to find the best violation of this inequality, and it's given, well, it's 4/3 on the left-hand side, which is not smaller than 1, right? So this is the violation. This inequality has an interpretation, or it may have more than one interpretation, right? So one way of interpreting this is thinking of the CHSH scenario again, because you have 4 different measurements. But instead of having just the compatible measurements between Alice and Bob, you also have these statements on the overlaps between the settings of Alice and between the settings of Bob. Okay, so we can write this as an inequality that relates the expectation values of the things that you actually measure by doing measurements at Alice and Bob on an entangled state with the compatibility of the measurements that Alice can have and that Bob can have, right? So this is the relationship between expectation values of what you measure in a belt test and compatibility of the different measurements that you do at Alice and at Bob. Right? So this is one way of interpreting these inequalities. But this is still a very recent work, right? So we're still working on interpreting these inequalities in different ways and finding the Bell inequalities corresponding to them and looking for more interesting results, right, of new inequalities of this type. The other examples I wanted to show are examples for 5 states. So you can list all the facets for 5 states, and we're still working on categorizing these facets. And this is work that our student, Rafael Wagner, is starting to do with us. So this is a pretty well-symmetric inequality in which you have the sum of all the overlaps in green between these 5 states, 5 measurements, minus the sum of the overlaps in red, smaller than or equal to 2. And when you try to maximize this with quantum mechanics, you find that you have exactly a regular pentagon on a great circle of the Bloch sphere. So you don't need higher dimensional states. You maximally violate this using qubit states, okay? And this other facet, other type of facet of the K5 graph, the violating states are these blue dots on the Bloch sphere. It's also qubit states. And you just have the sum of green again, minus the sum of red, smaller than or equal to 2. And quantum mechanics for these states here give you 9 quarters, okay, which is, of course, larger than 2. So there are many other types of facet that appears. The coefficients do not need to be 1 and minus 1, okay? You have other coefficients showing up, 3 and 2 and so on for this 5-state scenario. And it's interesting to look at what interpretation these may have in terms of either pure belt tests or contextuality tests or some mixed scenarios of the type that some recent works have been investigating, like Marcelo Terracunha and Rafael Rabelo, looking at both mixed contextuality and nonlocality scenarios, right? So they are well described by this kind of inequalities. So this kind of approach that I'm describing, you have different interpretations for the same inequalities, either as coherence witnesses between states or contextuality and nonlocality arguments between projectors, okay, measurements that you can do. So this is quite interesting because it's relating to very different notions of non-classicality, right? And these overlap inequalities, they're quite broad. You can talk a lot using this language because one overlap is the probability of a quantum measurement, right? The overlap is the probability of preparing one state and projecting it onto a different projector. So this seems to be broad enough, right? That you may be able to describe many different things, like I was telling you before, compatibility and expectation values in the same inequality. So this is a different derivation of the CHSH inequality with a different graph that gives you the same inequality. But now you have a graph with a vertex in the middle, which is represents the preparation, the maximum entangled state, the single state. And the 4 vertices in the around represent projectors onto the joint projector of Alice and Bob, okay? So it's a 2-outcome projector on a 4-dimensional space. So you have 4 different settings, and these are the 4 projectors that you have. So now I have 2 different interpretations for the overlaps again. The orange ones are probabilities of preparing these states and projecting onto either this, or that, right? The 4 possibilities. And the green ones, they are just the overlaps between the settings of Bob, here and here, or Alice, the vertical ones, right? And if you work out what the inequalities are here, you just have to add the 4 3-cycle inequalities, okay, for these 4 triangles we have here, and you get again the CHSH inequality independently of the overlaps, so they cancel out, okay, of the blue overlaps, which have to do with the compatibility of Alice and Bob. So you recover CHSH inequality independently of the compatibility conditions. So this whole idea lets you explore lots of things, right? You can ask for the zero-sum bounds because the optimization involved is much simpler. You have a finite dimension, which is just related with the number of states you have in the scenario. There are equivalences between protocols, which use either contextuality or quantum communication or coherent states, right? And it enables us to think about formulating unified resource theories for both coherence and contextuality and non-locality. So this is quite exciting. We're still at the beginning of exploring these things. So I'm coming to the conclusion. We've seen that we introduced basis-independent coherence witnesses. So it's a new concept, I guess, based on overlaps. We even measured them on photonic experiments. We have bounds on overlaps for coherence-free states. In these bounds, we show that they are non-contextuality inequalities and non-locality also. And this allows us to describe contextuality and coherence in a single framework. So this is helpful to discuss resources for quantum computation advantage. So that's one direction in which we want to push this forward. And I'd like to, before finishing, just raise some issues, okay, some ideas, throw these ideas to the people who are watching here. I'm pretty convinced there's a relationship with the PBR theorem, right? Because we are putting bounds on overlaps, and that's the key to the PBR result, Pusey-Barrett Rudolph theorem. So I'd like to flesh out what the connection is. It would be interesting to describe this in the contextuality by default framework, because we are talking about probability distributions, right? That's the basic thing we consider. It would be interesting to find new Bell and non-contextuality inequality and contextuality inequalities in their quantum bounds, and even check if we are what assumptions we're using, and whether we can find the zero-sum bounds of Bell tests by doing a much simpler optimization over these overlap inequalities, right? On this different way of thinking of the problem. And it's also interesting to think about the foundational importance of higher order Bargmann invariants, because you can measure these higher order Bargmann invariants, and I guess they will be useful and interesting to discuss non-classicality as well. So that's what I wanted to tell you, and I'm open to questions. Thank you for your attention.